So, hello everyone. Today we are going to be reviewing the paper with the title Symmetry-protected self-correcting quantum memories. Alright, so quantum correcting codes can be used to protect information in a noisy quantum computer, and it's theoretically possible for these codes to be self-correcting as well. So, in seeking models for self-correction, inspiration has been drawn from recent advances in our understanding of topologically ordered spin lattices. Now, if global symmetry is imposed on a model, the system can develop new quantum phases, and this has led to new types of phases such as Sbt and Sat phases, which we'll be seeing soon. In this paper, it is shown that such phases can support self-correcting quantum memory, so SEQMs in 3 dimensions. Two examples of such models are also studied, which are the RBH model and the gauge color code, which we'll be seeing soon. Now let's look at a brief background on SEQMs, or self-correcting quantum memories. The requirements of a SEQM has been formalized by the so-called Caltech groups. That is, an SEQM in d spatial dimensions is a quantum many-body spin system with the following properties. The Hilbert space consists of a finite density of finite dimensional spins. The Hamiltonian has local terms with bounded strength and range, such that each spin is in the support of only a constant number of terms. The ground space of H is degenerate, such that a qubit can be encoded in the ground space, and this ground space is also stable to perturbations. And finally, most importantly, the lifetime of the stored information after coupling the system to a thermal bath must go without bound in the system size. And we'll be showing that it goes exponentially with the system size. Now, the central question for candidate SEQM is how long the encoded information can undergo thermal evolution, that is, be exposed to the surrounding, while still being recoverable. The standard approach to modeling thermalization is to couple the system to a thermal bosonic bath. And yeah, thermalization is modeled by this equation over here, where H full is the Hamiltonian of the whole universe, system plus surrounding. H is the Hamiltonian of the system, H bath is the Hamiltonian of the bath, and the remaining are the interaction terms, where S alpha and B alpha are the local operators acting on the system and the bath side, and lambda is a coupling constant, which is usually less than 1. Now, assume that the state is initialized as rho naught. After some time, it evolves to rho t. We wish to recover rho 0 from rho t, which can be done by error correction. And it consists of 2 steps. Firstly, a sequence of measurements is performed on the noisy state to obtain an error syndrome. Then a recovery map is performed that depends on the syndrome. The net action of the syndrome measurement and the recovery map can be condensed into a single map, that is phi EC. And for a fixed error rate epsilon, we can define the memory time tau mem as the maximum time for which this inequality over here, which is the norm of the phi EC vector from rho t to rho 0, is satisfied. This less than epsilon is satisfied. This gives us a measure of the memory lifetime of an SEQ, which ideally should go with system size. And you can see that, like, if you solve this equation, it will lead to an exponential growth with system size for tau mem. Now let's look briefly about topological phases with symmetry. Quantum phases of matter are characterized by their ground state properties. When symmetry is at play, the classification becomes richer, as all Hamiltonians in the family must respect the symmetry. In particular, it's possible that two Hamiltonians that are equivalent in the absence of symmetry become inequivalent in the presence of the symmetry. This leads to the notion of Sbt and Sat phases. Now we assume that a system has symmetry described by a group G, the unitary representation S. And consider lattice lambda in d dimensions with a capital D dimensional spin placed at each side, I belonging to lambda, each side of the lattice. We say two gapped Hamiltonians with symmetry S of G belong to the same phase if there exists a continuous path of gapped local Hamiltonians from H0 to H1 that all obeys the symmetry S of G. Now for SPT and SET ordered systems, one commonly considers global symmetries that act via an onsite fashion on the underlying degrees of freedom. That can be expressed by this following equation, where U of G is a local side independent representation of G. Now let's take a look at Spd phases. These are defined as the class of symmetric Hamiltonians which are equivalent under local symmetric transformations. They do not close the gap and are not in the same class as the trivial phase. Here in this slide you can see the difference between a non-trivial phase and a trivial phase. So basically Spd phases are not in the same class as the trivial phase when symmetry is enforced. And the SET phases are defined as the Hamiltonian that is distinct from the trivial phase even without any symmetry constraint. And these 2D SET phases appear naturally on the boundary of 3D Spd phases. Now, the relationship between self-correction and thermal stability or topological order is complex. While we do not yet have a general result connecting these two, we can explore the connection between these two further through the example of the RBH model that we'll be seeing soon. Now let's take a brief look at higher form symmetries. We'll be making use of these higher form symmetries for the future topics. A Q-form symmetry is given by a symmetry operator associated with every closed codimension Q submanifold of the lattice lambda. And the symmetry operators are given by this equation over here. You can see that it's similar to the equation that we had for describing the symmetry operators of the Sbt and Sat ordered systems. And of particular interest for us in this paper will be one-form symmetries in 3D systems, which are the next weakest generalization of the conventional global onsite symmetry. So now let's move on to the second example that is studied in the paper, which is the gauge color code in 3D. The gauge color code is an example of a topological subsystem code, which means in addition to local logical degrees of freedom, subsystem codes also contain redundant gauge degrees of freedom that are not used to encode information. A subsystem code is specified by subgroup G of the polygroup known as the gauge group. A stabilizer group S for the subsystem code can be defined by choosing any maximal subgroup of the center Z of the gauge group such that minus identity does not belong to S. The code space CS is defined as the mutual +1 eigenspace of all elements of S. The information that we want to code is only encoded into the subsystem of CS that is invariant under all gauge operators G belonging to the gauge group. Now the gauge color code lattice are defined on lattices known as 3-colexes. In particular, a 3-colex is the result of gluing together 3 cells polyhedrals such that each vertex is 4-valent and 4-colorable. Now by 4-valent, here we mean each vertex belongs to 4 edges, and 4-colorable meaning each polyhedral 3 cell can be given 1 of 4 colors such that the neighboring 3 cells are differently colored. And we can choose these 4 colors to be labeled as I, B, G and Y for red, blue, green and yellow. Now we note that similar to the RPH model, the gauge color must have boundaries. The gauge color code must have boundaries in order to possess a non-trivial subspace. For concreteness, we choose these boundary conditions to be the tetrahedral boundary conditions. So the 3D gauge color code. For each vertex of the lattice tetrahedral colex C3, we place a cube. We have an X and Z gauge generator for each face of the lattice given by this equation here, where GXF and GZF are poly operators supported on the face F. The stabilizers of the code are given by the X and Z on the 3 cells of the lattice given by this equation here. SXQ and SZQ are the poly operators supported on 3 cells. Now with the aforementioned boundary conditions, the code encodes one logical qubit. The bare logical operators for this qubit can be taken similarly to the RBH model. We are therefore justified in viewing the logical information as being encoded on the boundary, as we would get with the 2D SAT model, which is encoded on the boundary of 3D Spd model. Now we can define an exactly solvable Hamiltonian by this equation, where GB is given by this set and KF denotes the color of face F. The commuting model HGB here defined here without any symmetric constraints is easily shown to be disordered at any non-zero temperature because it's just a collection of uncoupled 2D color codes, that is 2D SET codes or symmetry-enriched topological codes. Now this Hamiltonian HGB has a Z22 one-form symmetry given by the stabilizer group S, which was described before. This one-form symmetry couples the bulk and boundary excitations, as was the case in the RBH model. Now the argument for the symmetric energy barrier to self-correction follows identically to that of the RBH model. That is, provided the temperature is sufficiently low, information can be stored for a time that grows exponentially with the system size. As a result, our stabilizer model, based on the 3D gauge color code, protected by Z22 one-form symmetry, provides another example of a self-correcting quantum memory. That's been it from me. Thank you for watching and have a great day.